to the second plenary of the 59th meeting of the Australian Math Society Annual Conference. My name is Leslie Ward and I'm the chair of the Women in Mathematics Special Interest Group of the Society. And it has fallen to me to introduce this year's Hannah Neumann lecturer, Frances Kirwan. But first I'd like to say a few words about Hannah Neumann. Hannah grew up in Germany and moved to Britain before the war with her husband Bernard Neumann, who, as you may know, was interned in Britain during the war since he was a German national, although he had left Germany because of his Jewish heritage. And Hannah had a very fascinating early life that many of you may know the details of much better than I do, but it did involve a stint living in a caravan in England with several of their five children while Bernard was interned. Later on, I think at least 3 of those 5 children grew up to be mathematicians. The Neumanns moved to Australia in about 1965 when Hannah came to the ANU as Professor of Mathematics in the then School of General Studies, and she was the first woman to be appointed as a Professor of Mathematics in Australia. The second was not until 18 years later, in 1983. Hannah worked in group theory and wrote many papers and had many students who went on to have successful careers themselves. Hannah was an inspiration and a model for many mathematicians, including many women mathematicians. I myself was awarded the Hannah Neumann Prize as an undergraduate at ANU, and there are many other things named in her honour. She also has the possibly unique distinction of having not 1 but 2 named lectureships of different professional societies in Australia named after her. There is this one, for which we're gathered here today, and there is also the Hannah Neumann Lectureship at the Australian Association of Mathematics Teachers. And that reflects Hannah's long-standing involvement with the teaching of mathematics at secondary school level, about which she had thought deeply and made many contributions as well. So I also would like to mention that this is the 5th year that we've had the Hannah Neumann Lecture among the plenary lectures of the AustNS, and previous speakers were Nina Snaith, Nalini Joshi, Cheryl Prager, and we'll just pass quickly on that. You can find the speakers listed on the website of the Hannah Neumann Lectureship, which hangs off the WILSEG website. So Hannah was quite a force in Australian mathematics in more ways than one. Let me turn to today's speaker, Professor Dame Frances Kirwan of the University of Oxford, who works in algebraic and symplectic geometry. Dame Frances Kirwan has held many honours. She's currently on the Council of the Royal Society, and she's the chair of the Council of the UK Mathematics Trust, which is the equivalent of the Australian Mathematics Trust, so that's another link with Hannah's interests there. Frances is a former president of the London Mathematical Society, and one of the many projects she was involved in there was developing the LMS's good practice scheme for building successful and diverse and well-functioning mathematics departments across the UK. She is also a former coordinator of the European Women in Mathematics Network. And I know that Frances has a personal connection with Hannah Neumann as well, but she's going to talk about that herself. So without further ado, I invite you to join me in listening to Frances' lecture, which his title is up there.
Thank you very much, Leslie, for a kind introduction. So it is a great honour to be invited to give the Hannah Neumann lecture. Can I just check, is the microphone working all right? Yes? Good, thank you. So I never met Hannah Neumann, who died sadly in her 50s, I think. But her eldest son, Peter, has been a hugely supportive colleague and friend, more or less throughout my mathematical career. So So it's a particular pleasure for me to be invited to give this lecture. So, before starting, I want to apologise, first of all, that I seem to have managed to leave out the final word in my title from the version which went into the programme, so apologies for that. Also for the fact that I've got a horrible cold at the moment, so I hope I get through the hour without coughing too much or indeed infecting all of you. And the final thing I wanted to mention before starting is the dreaded four-letter D word. So I think this morning I've been called Dame Frances more times in a few hours than in the whole of my life before. So it seems that politicians like it, so that's fine, but it always makes me think of Dame Edna Edwards. So, blossoms, I just want to make sure that all of you here are well aware that if anyone from now on calls me Dame Frances, then I will assume that you're very annoyed with me about something or other. So I think I've got everyone at home trained. Right, so what I want to talk about is a problem that comes up in algebraic geometry and something that's been core to my research really throughout my career. Lots of other people have made huge contributions, not least my collaborators. So the motivation for trying to construct and study quotients of algebraic varieties by linear algebraic group actions really comes from, well, for me at least, comes from moduli problems in algebraic geometry and trying to understand, construct and understand moduli spaces. So just as a quick reminder, or to tell you a little bit about moduli problems, where moduli spaces come from, they come from classification problems. So classification problems in geometry, typically you can't just write lists of the objects that you want to classify, even infinite lists. So typically objects are parameterized by parameters involving complex numbers if you work over complex numbers. So the usual sort of setup of ingredients for a moduli problem is that you have some sort of objects. So, for example, compact Riemann surfaces that you want to classify. You have some sort of equivalence relation. So, for example, you might want to classify them up to biholomorphism. And also, technically, you need to know what you mean by a family of these objects parameterized by a base space, so some sort of parameter space. So typically that might be given by a surjective map, nice map of some sort, going to the base space, the parameter space, with the inverse image of a point, the object parameterized by that point. So, I have a this is making strange noises. I don't know if it was a bad idea to put it around my neck. Let's try it hanging down. So, what we typically want to do is we want to fix any discrete invariants that you might be able to spot for the objects that you want to classify. So if it's compact Riemann surfaces, then the obvious discrete invariant is the genus, the topological invariant. And then roughly speaking, the moduli space is just the set of equivalent classes of objects with some sort of nice geometric structure that ought to be that ought to come out of the ingredients, and in particular ought to come out of knowing what you mean by a family of these objects parameterized by a base space. So that's what a moduli space is very roughly, and very often they arise in algebraic geometry and other parts of geometry indeed, as some sort of parameter space quotiented by a group action. So typically there might be an obvious way to parameterize the objects that you're interested in, or maybe a not so obvious way, but some way of parameterizing them. But typically that parameterization may have some redundancy, and the redundancy may well be given by a group action. So you have two sets of parameters giving isomorphic objects or equivalent objects, even only if they lie in the same orbit for some group action. So, well, a very, very simple example, obviously, is a clock where you take the real line as parameterizing time, and then you quotient it by translation by the integers, where the unit is, I guess, traditionally 12 hours, and the result is the circle, one-dimensional sphere, and that's why the clock is circular, of course. But something that comes up is much more, well, fundamental in algebraic geometry over complex numbers is projective space. So complex projective space, of course, you can think of either as a unit sphere in Cn plus 1, if you're working over complex numbers, quotiented by the circle, or as non-zero points in Cn plus 1 quotiented by C star multiplication. Yes, so as I said, moduli space is often constructed as quotients of algebraic varieties, some sort of parameter space, by actions of linear algebraic groups. And so linear algebraic groups, so groups of matrices essentially. You have unipotent groups, which you can think of as sort of upper triangular groups of upper triangular matrices, strictly upper triangular matrices. And any linear algebraic group is an extension of its unipotent radical, which is maximal normal connected, I guess, unipotent subgroup, by a reductive group, which is one whose unipotent radical is trivial. So reductive groups, for example, general linear groups, special linear groups, products of these. And if we're working over complex numbers, which I want to do for simplicity, because I'm not very familiar with working over finite fields and so on, I want to work over complex numbers, then the group is reductive, if and only if you can think of it as the complexification of a maximal compact subgroup, so of a compact group. So roughly speaking, that means that you've got this compact subgroup, and the Lie algebra is just the tensor of the algebra of the compact group with the complex numbers over the reals. So general linear group is the complexification of unitary group, for example. So we have both reductive groups and non-reductive groups turning up naturally as the sort of groups that you might want to quotient by when you are constructing moduli spaces in algebraic geometry. So in particular, if you're thinking about objects sitting inside a complex projective space or a complex affine space, then you might well be wanting to quotient by the automorphism group of, say, complex projective space, which is just the projective general linear group, and that's a reductive group. On the other hand, if we look at more complicated algebraic varieties and their automorphism groups, then we can typically get non-reductive examples. So suppose you were interested in hypersurfaces sitting in not a projective space but a weighted projective space. So say the weighted projective plane here, which is just with weights 1, 1 and 2. So you take C3, take away the origin, and you quotient by C star, but where the action is not just by scale multiplication, but with weights 1, 1, and 2, say, then if you look at the automorphism group of that, it's not reductive. It's got a unipotent radical, which is, oops, sorry, that's not what I meant to do. Pointer, there we go. So you've got a unipotent radical, which is isomorphic to complex numbers under addition, 3 copies of, and that's occurring because you can take any point in projective space and you can add to the final coordinate that has weight 2 any quadratic expression in the 2 coordinates that have weight 1. So, so that gives you the unipotent radical, and then there's the reductive part, which is essentially just the GL2 acting on the weight space of dimension 2 with weight 1. So, so we get an automorphism group which is not reductive, and so you might want to quotientify a group like that if you were constructing, say, a moduli space of hypersurfaces in this weighted projective plane. So, the thing about these sort of linear algebraic groups, say over the complex numbers, is that they are essentially never compact. So the simplistic reductive example is C star, the simplest non-reductive example, unipotent example is C plus complex numbers under addition. And so when they act, when these groups act on algebraic varieties, the orbits are typically not closed. So, for example, if C star acts on Cn plus 1 by scalar multiplication, then the origin by itself forms an orbit which is contained in the closure of every other orbit. So, if you just try to take an ordinary topological quotient, then you'll get something that doesn't have a nice geometric structure. So in the classical topology, it's certainly not Hausdorff, and so you can't hope to make it into a nice algebraic variety. On the other hand, if you throw out that bad orbit, which is given by the origin that lives in the closure of every other orbit, then you do get a nice quotient, which is just projective space, and it has a nice geometric structure, and everything is good. So the basic idea of Mumford's geometric invariant theory, which he developed in the 1960s, with the main motivation wanting to construct and study moduli spaces, is that if your group, the group that's acting as a reductive group, then Mumford's GIT, geometric invariant theory, tells you how you can find some bad orbits, like the origin in this case, which you can throw out in such a way that once you've thrown out these bad orbits, then you are able to construct a nice quotient variety, which will actually be itself an algebraic variety of the remaining part, which is the stable part. So, so yes, so as I've said, moduli spaces in algebraic geometry don't always exist, but if they exist, we can often construct them as quotients of algebraic varieties by group actions. And if the groups are reductive, then we can use Mumford's geometric invariant theory to construct them and study them. And also we can use some techniques from symplectic geometry, which I'll talk about later if I have time. So in a moment, I want to review the classical reductive GIT, but what I want to then go on to do after that is to think about what happens if the groups are not necessarily reductive. So, as I said, for example, moduli spaces and hypersurfaces in toric varieties. So, for a weighted projective plane, as we saw, you get a non-reductive automorphism group, and for any toric variety, you can explicitly describe the automorphism group, and typically it will be not reductive. So, so that's one example. Another motivation comes from singularity theory and looking at jet differentials and bundles of k-jets of, for example, polymorphic curves, jets of polymorphic curves in a complex manifold, where you, so if you have a germ, two germs of polymorphic curves near a point at the same k-jet, it is essentially, it just means that you're looking at their Taylor expansions up to order k. And so then the natural group that acts and you might want to quotient by is the reparameterization group for k-jets of germs of bipolymorphisms of the complex of C based at the origin. And it's not too difficult to see that they form a group of matrices which have this this particular form. So so you have, sorry, pressing the wrong thing again. Matrices of this form where you've got a non-zero parameter A1 in the first place and then powers of it coming down the diagonal. And then below the diagonal you've just got zeros, and then along the top row you have other parameters which could be any complex numbers, A2 up to AK, and then above the diagonal you have some just polynomials in the parameters from the top row. So this is non-reductive, definitely it's unipotent radical, is just given by having just ones down the diagonal when the parameter A1 is 1. And it's the semi-direct product of its unipotent radical with the C star, which is just given by the other parameters being 0 and A1 not. So again, we've got a non-reductive group that we might want to be able to quotient by. So, but back to say a bit about the reductive setup and classical GIT. So now let's have a complex reductive group. So this basically, well, certainly works over algebraically closed fields of characteristic 0, and most of this will work in other characteristics as well, but for simplicity, let's work with complex numbers. And let's suppose this complex reductive group is acting on a complex projective variety. And in order to get geometric invariant theory started, then Montfort needs what's called a linearization of the action, which is an ample line bubble on X, technically, and a lift of the action to the ample line bubble. But basically, we can just think of X as being embedded in some projective space, and the action is just given by a linear representation of the group to GL n+1. And so then we can use the sort of basis of algebraic geometry, which is that you go back and forth between the geometric objects and the algebraic objects. So associated to X, or strictly speaking associated to X and the line bundle, we get a graded complex algebra, a finitely generated graded complex algebra, just essentially polynomials on polynomial functions or sections of the line bundle quotiented by the ideal generated by the homogeneous polynomials that vanish on X. And so, roughly speaking, the elements of this thing look like functions on X. Well, they're really sections of line bundles, but roughly speaking, you'd expect that functions on a quotient should correspond to invariant functions on the original space. So the idea is that you look at the invariants, the G invariants in this graded algebra, and the point about having a linearization is that you are given a lift of the action to L, which gives you an induced action on this graded algebra. So you look at the invariants, and if the group is reductive, then that algebra of invariance is itself finitely generated. So that means that it in turn corresponds to a projective variety, which we think of as being the quotient in the sense of geometric invariant theory, really associated to the linearization as well as the group action. But so so if necessary, you should put that in the notation, but it depends on the choice of linearization. So that's the basic setup, but then what you want to do is you want to understand what the geometry of this algebraically, this projective variety, which is playing the role of the quotient, looks like. So, associated to the inclusion of the algebra invariance in the original algebra, we get a rational map in the other direction. So, it may not be everywhere defined because it's defined by the ratio of invariant polynomials, and if those invariant polynomials all vanish simultaneously, you don't necessarily have a well-defined map, but you get a rational map. And so then that rational map fits into a diagram which I'm going to put over here because it's a sort of fundamental diagram for what I want to talk about. So we have the rational map going to the GIT quotient, and I should say that it's traditionally written with 2 slashes because it's not just a quotient in the sense of topological quotient. So, and this is a complex projective variety, but then if we restrict to a suitable open subset of X called the semi-stable points, then this rational map becomes well-defined polymorphism, and it's a G-invariant map from the semi-stable set to the quotient variety, the GIT quotient. It turns out that it is it's actually surjective. It's onto. That's not at all obvious, but it is the case. But it's not necessarily, this quotient is still not necessarily just the topological quotient of the semi-stable set by the group actions, so we still might need to identify different orbits here in the quotient variety. But if you restrict to a smaller open subset called the stable points, then you really do get a nice geometric quotient which has all the properties that you would want a quotient to have, and this is just an open subset of the GIT quotient, the projective variety. So what we've got here is a way of finding the at least an open set of stable points, a G-invariant open set of stable points, where we can find a nice quotient which is a quasi-projective variety, and we also have a way to find an actual projective completion of it. And we'd also like to know a bit about what this quotient variety looks like geometrically, because as I said, it's not in general just a topological quotient, but it turns out that it turns out that 2 points in 2 semi-stable points get glued to the same, get sent to the same point in the quotient variety, even only if the closures of their orbits meet in the semi-stable set. So it's obvious that if this happens, then they must get sent to the same point because the map is G-invariant and continuous. But in fact, it's an if and only if. So you have that topologically you can think of this quotient variety as the semi-stable points quotiented by this equivalence relation, where 2 things are equivalent if the closures of the orbits in the semi-stable set meet. And so, if I have time, I'll come back to this later, but in the reductive setup, in the complex algebraic geometry over complex numbers setup, if in the reductive case that we're looking at, then we've got, as I said, the group is the complexification of a maximal compact subgroup, and another way of understanding the geometry of this quotient is using symplectic geometry, and you can describe it as the zero locus of a of a suitable moment map quotiented by the compact group. So there are different ways of thinking about what this situation looks like geometrically. So the other really important thing that makes Mumford's geometric invariant theory really powerful is that there are ways of working out which points are stable and which points are semi-stable for a given action and linearization without having to know in advance what all the invariants are. Because in general, working out what the invariants are is a very difficult problem, and in principle the semi-stable set and the stable set are defined in terms of having invariants with suitable properties. But luckily, there is this very nice way of actually working out what the stable set and the semi-stable set are without having to know what the invariants are. So, first of all, you look at a maximal torus. A complex torus, so products of C stars and maximal one sitting inside G, and they're all unique up to conjugation. And for stability and semi-stability for the maximal torus, you just have to, you can just choose homogeneous coordinates so that on the ambient projective space, so that the torus is acting diagonally with given weights. You can think of the weights as being represented by elements of the dual of the Lie algebra of the torus, and you've just got finitely many weights. And for a point with coordinates, homogeneous coordinates x0 up to xn in x, we just look at those weights corresponding to the coordinates which are non-zero in x, and we look at the convex hull of that set of weights, and it's just a question of whether 0 lies in that convex hull or in the interior of that convex hull. So that's often pretty easy to work out. And then semi-stability or stability for the action of the whole group G, you just take the, for semi-stability, for example, you just have to look at the points which are not semi-stable for the torus and then sweep out by the action of the group. So, and similarly for stability. So, that's the other really powerful thing that makes GIT work. So we have these Hilbert-Mumford criteria. For semi-stability and stability. So, in principle, given a linear action, we can work out what the semi-stable points are, we can work out what the stable points are, we can then describe this geometric quotient, and also by looking at closures of semi-stable orbits, we can give some sort of geometric description for the projective completion. So, what happens if the group is not reductive? Well, we can't just do what Mumford did for reductive GIT, because we get stuck at the first stage, because we don't necessarily know that this graded algebra of invariance is finitely generated. So that means that it will determine some rather nasty sort of projective scheme, but it won't give us necessarily a projective variety. So what we'd like to do is define some sort of sensible quotient variety when G is not necessarily reductive, and most importantly, trying to understand it geometrically. And so I'm just going to skim over this. So with collaborating with a student, we have a sort of an analogue of this picture for the non-reductive setup, but so basically we have some sort of variety which we call an enveloping quotient. We have we can define a semi-stable set and a stable set with a nice geometric quotient of the stable set. But basically all the nice things that make reductive GIT so powerful in general fail in the non-reductive setup. So this map from the semi-stable set to the quotient variety is not in general surjective. The quotient variety is itself not necessarily projective, though if the invariants happen to be finitely generated, then it will be just the projective variety associated to the invariants, but in general it won't necessarily be projective. And there are no obvious ways in general of finding analogues of the Hilbert-Mumford criteria for stability and semi-stability. So in the last 6 months to a year, we've actually made some nice progress here, which is quite technical and I'm not going to talk about today, but it turns out that if we generalize slightly what we mean by a linearization to allow a bit more flexibility, and then for this slightly generalized version of linearization, we can talk about semi-stability and stability and have again this sort of picture. And it turns out that then for lots of situations, including actions of automorphism groups of any toric variety, and also including the jet differentials case that I mentioned earlier, there are nice ways of defining semi-stable sets, stable sets that are given by Hilbert-Mumford type criteria that you can work out, and you get a nice geometric quotient of the stable set, and you get a nice projective completion of the geometric quotient of the stable set. So even in, for example, for those of you who know about it, the famous Nagata counterexample, which was the first counterexample given in the 1950s for Hilbert's 14th problem. So it's an example where the invariants are not finitely generated. This new way of thinking about things does give us a very nice picture where we don't actually get projective variety associated to the invariants, the full invariants, because that wouldn't give us anything nice. But there's a nice way to basically choose some of the invariants where everything works nicely. But, so I don't want to talk about that. I want to spend the last little bit of my talk talking about links with symplectic geometry and indeed hypercalar geometry, if I have a little bit of time to do that at the end. But before I do that, let's look at an example where we can actually understand what's going on geometrically in a non-reductive setup, because we can turn it into a question about a reductive group. So this is where we have the additive group, C+, acting on projective space, so the full projective space. And then because we can, basically because of Jordan canonical form, we can choose a way to extend the C+ action to an SL2 action, where you're thinking of C+ as just being the upper triangular matrices in SL2. So, because we've got this extension of the C+ action to an SL2 action, it turns out that in fact this means that in this case the invariants are finitely generated, so this is the Weizsäcker theorem. So we can define our non-reductive GIT quotient as just the projective variety associated to the invariants. And the reason is essentially that we're looking at C+ invariants on Pn. Roughly speaking, those correspond to G invariants where G is SL2, on this sort of twisted product, G cross Pn quotiented by the diagonal action of C plus, and there's no problem taking quotient there because the C plus action on G is free and so on. And because the C plus action on Pn extends to a G equals SL2 action, you can see that as a G space, this is just the same as the untwisted product of G mod C plus with projective space. G SL2 mod C plus, we know, is just C2 minus the origin with the usual action of SL2. It's just one orbit, and the stabilizer of a particular point is this C plus. So we've got C2 minus the origin across projective space. And then we can just use Hartog's theorem. So these invariants, they're all holomorphic things. They just don't see the missing origin, which is codimension 2. So they will extend automatically over the origin in C2. So we basically are looking at G invariants on C2 across projective space at the end. And then if you choose the linearization appropriately, you can then actually replace the C2 by P2. So it turns out that you can describe, well, so then you've got finitely generated invariants because you've now reduced yourself to a reductive group SL2 acting on, well, projective variety or product of affine and projective. So that tells you that you do get finitely generated invariants in this situation, and moreover you can describe them in terms of reductive GIT by looking at this SL2 action. And as I said, you can turn the C2 into a P2, and you can understand explicitly why this map from the semi-stable point to the GIT quotient fails to be onto. It's basically because of the missing 0 in C2 minus the origin, which the invariants don't see is missing. And so you can look at some examples and explicitly see that it won't be surjective. And other examples show that the image is not even necessarily a variety. So you can't just get rid of the lack of surjectivity by saying, well, we'll define the GIT quotient to be the image, because that won't necessarily give you a variety. Okay, so then the link with symplectic geometry, just very quickly. So if you've got a complex algebraic variety, then complex projective variety, then it will have a Kähler structure coming from sitting inside complex projective space, and that will give you a symplectic structure in particular. So you get a closed non-degenerate 2 form. The standard example of symplectic manifold is just a cotangent bundle. And if you take a compact Lie group acting on a symplectic manifold, then you can ask for something called a moment map or momentum map, which is a generalization of ideas of angular momentum and linear momentum from mechanics and so on. And it turns out that in the case that we're interested in, so moment maps don't always exist, but in the case that we're interested in, then they do. And if you're in this a Kähler situation, then if you've got a moment map, then the action will extend to the complexification. So in this situation, the natural sort of quotient to take is, again, you can't just take the ordinary topological quotient, because that will not necessarily inherit a symplectic structure, because, for example, there's no need for it to be even dimensional, and symplectic manifolds are always even dimensional. But if you take the inverse image of 0 under the moment map and quotient by the compact group, then you do get an induced symplectic structure on this thing. You might have some singularities, but it's a stratified symplectic space. And it turns out that in the Kähler case, you can sort of link this up with with the complex geometry, taking quotient of an open subset of your Kähler manifold by the complexified group. And indeed, if in the reductive GIT set up over the complex numbers, it turns out that this symplectic quotient, which I've written with slightly different quotient sign by the compact group, is the same as the GIT quotient by the complexified group. So, for example, if we take 4 points on P1, with K is just SU2 acting as rotations on the sphere, and the complexified group just essentially Mobius transformations, then you find that the stable points are the points where all 4 points are distinct, and the quotient is just P1 with 3 points removed. You can see that by the cross ratio. And the semi-stable points are the points where at most 2 of the 4 points are allowed to coincide. And so that gives you 9 possibilities, because you can have 2 and 2 coinciding, or these 2 coinciding, these 2 not, or 2 and 2 coinciding, for the 3 different ways of splitting 4 points into 2 pairs. And those map down to the 3 missing points in P1, so the GIT quotient is just P1. And the moment map here is essentially given by the centre of gravity of the 4 points. And so from the symplectic quotient point of view, you're looking at balanced configurations of points on S2. And you can sort of, so as long as the points are all distinct, then you can use a Mobius transformation to move them into a balanced configuration. If you've got more than 2 coinciding, you certainly can't. If you've got 2 coinciding, then you can, at least in the limit, the closure of the orbit, there will be a point where a configuration which is balanced, where you've got 2 and then the other 2 at the antipodal point. So that's the link in the reductive setup with symplectic geometry. So then there's this nice construction called symplectic implosion, which is due to Gilman, Jeffrey, and Shamar 15 years ago, or so it was published. And so this is the same sort of setup, but now instead of taking the inverse image of 0 under the moment map and quotienting by the compact group, what we do is we look at the inverse image of the positive Wahl chamber. So remember in the so for SU3, for example, we have a picture with our positive Wahl chamber like that. And if you take the inverse image of the positive Wahl chamber, and then you do some, under the moment map, and then you do some collapsing on the boundary. So the collapsing on the boundary is given by essentially the commutator subgroups of the stabilizers of the points on the boundary of the positive Wahl chamber under the coadjoint action. Then, remarkably, it turns out that that has a nice symplectic structure, and indeed, often it has a nice structure of an algebraic variety. So, running out of time, so I will go very fast through this. But in particular, we can look at the so-called universal implosion or imploded cross-section, which is the implosion of the cotangent bundle of the group itself, the compact group, by the action by left translation. And it turns out that then this imploded cross-section, you can get any other implosion by taking, you can take the product of your symplectic manifold X with the imploded cross-section, the universal imploded cross-section, and then take the symplectic quotient of that product by the diagonal action of K. So, so you get this, this implosion which always inherits a action of the maximal torus, and it has the property that if you quotient the implosion by the torus, or you take the reduction, symplectic reduction by the torus, then that recovers the original reduction, symplectic reduction, by the compact group. So it's some sort of abelianization in some sense. And in the SU2 case, we, lo and behold, what we end up with is just the C2 minus the origin together with the point corresponding to the boundary of the positive bar chamber, giving us our C2 again, which is just as we had in the example of the C plus action. And it turns out that that's not a coincidence. So, so the link, there's a really nice link with algebraic geometry and Kähler geometry, which is that the universal implosion can be identified with what's called the canonical affine completion of the quotient of the complexified group by a maximal unipotent subgroup. So in particular in the SL2 case, the maximal unipotent subgroup we can just take as the C plus that we were looking at before. So there's this nice link, it turns out, in this particular situation, if you've got a projective variety acted on by the complexification of K, or a complex reductive group, then the implosion can be identified with the non-reductive GIT quotient by maximal unipotent of the reductive group. And that tells you that in this situation you get a really nice geometric description because the implosion construction is very nice. So that's the link with symplectic geometry, and then I really don't have time to talk about the hyperkähler setup, but hyperkähler geometry is really nice. So you have lots of complex structures, and in particular corresponding to I, J, and K, the quaternions, and you have to have a hyperkähler. Well, if you've got a nice group action, then you can talk about a hyperkähler moment map. You can talk about hyperkähler quotients, where you get an induced hyperkähler structure on the inverse image of 0 under the hyperkähler moment map and by the compact group. And now the reduction, the quotient has the dimension is reduced by 4 times the dimension of the compact group. And so one of the projects that we've been looking at in the last few years is an analogue of implosion for hyperkähler geometry. And I'm going to finish with this slide rather than talking in any more detail about it. But what the hyperkähler implosion of a hyperkähler manifold should be is some sort of stratified hyperkähler space with an induced action of the maximal torus, which is supposed to be some sort of abelianization of the original action. And we should be able to construct it using a universal hyperkähler implosion, which should be a stratified hyperkähler space with lots of nice properties. And then if we can define the universal hyperkähler implosion properly, then we can construct the general hyperkähler implosion in this sort of taking a product with the universal one and then taking the hyperkähler quotient by K. So, so one way of thinking about it, which is an analogue of fluid, which brings us back to the non-reductive geometric invariant theory, is that by looking at the properties of symplectic implosion, you realise that the universal hyperkähler implosion should be some sort of complex symplectic quotient of the cotangent bundle of the complexified group by maximal unipotent subgroup. So it turns out that the cotangent bundle of the complexified group really does have a nice hypercalar structure. So that's due to Kronheimer 25 years ago or so. And so what you would like to do is take the universal one it should be the hypercalar inclusion for that, and it should be basically, you want to take a complex symplectic quotient. So you impose by this maximal unipotent. So you impose the condition that the part in the dual of the algebra should actually be in the annihilator of the maximal unipotent, and then you want to take the GIT, the non-reductive GIT quotient of this by the maximal unipotent. So it should be something like this. But the problems are, first of all, it's not at all clear that such a nice geometric GIT, non-reductive GIT quotient exists. It's a nice, well, in this case, affine variety rather than projective. Whether you have finitely generated invariants. There's a question of whether it's hypercalar, because here we're sort of fixing complex structure and just working with complex structure, and also understanding its geometry. So progress has been made on that, but I will stop here, having run out of time. So many thanks for your attention.
I think in the interests of time, we'll just take one question from the floor, and we have a roving microphone. So is there a question for Frances?
Thank you. My question is about this last point, maybe inspired by the example of C+ that you gave before. Is there any way to, in general, embed that variety you take the quotient of there into something on which the whole of KC would act, and constructing that quotient and then finding this insight?
Yes, so that's very much what you would expect. So this, so as I said, when we're looking at these non-reductive GIT quotients, you don't expect the map in general from the semi-stable sets or whatever it is. I mean, in the affine case, everything's semi-stable, so we don't have to worry about that, but we don't expect the map to be surjected. And what happens in these sorts of situations is that you have, in this case, you have a nice quotient in the traditional sense, basically because the maximal